We're going to talk about imaginary numbers, and if we've never used them before, they can be pretty overwhelming. You could just study the pattern and memorize it, and that is something that will help you get through the booklets of work. But with the entire domain being a complex domain, I feel like understanding imaginary numbers better will help us work through this entire level. So we're going to go through and see what imaginary numbers are all about. The definition of imaginary number is I, for imaginary, equals the square root of -1. That's just what it is. Imaginary numbers are used to model the rotation of vectors, and we will talk a little bit more about what they are, where they came from, and everything. So in classical models, we use our 5 common topics: definition, comparison, relationship, circumstance, and testimony. We're going to use a lot of our definition, comparison, relationship in talking about this especially, and we may hit on some circumstance. And then, of course, testimony is that really anything that we know, we have gathered information from what other people have put out into the world, and we process it and come up with our own understanding of that information. We're going to compare negative numbers and complex numbers, okay? And it's going to include some fun facts and information about those negative numbers and complex numbers. So, fun fact would be the invented to answer. What were negative numbers invented to answer? Negative numbers were invented to answer what is the answer of less minus more, or something like 3 minus 4. Negative numbers have to exist to answer that. If you think of your bank account having $3 in the bank and you write a $4 check, you will be negative $1 in the hole. You've got to have negative numbers, especially in the world of finance. Or negative numbers are strange because how can you have less than nothing? Intuitive meaning is the word opposite. Considered absurd until the 1700s, the multiplication cycle or general pattern is 1, -1, 1, -1, or x, negative x, x, negative x. We know that because if we start off with a positive and we multiply it by a negative, we will get a negative. If we take 2 negatives and multiply them together, we will get a positive. If we take that positive and multiply it by a negative, we will get a negative number, and so on and so on. Use in coordinates, going backwards from origin. So we would start at nihilo, nothing, and we would go to the left or backward from that. And then we measure size with negative numbers by using absolute value. -4's absolute value is 4. It's 4 hops or movements away from the point of origin, away from nothing. And if we go over to the complex numbers, we are looking at, they were invented to answer the question, what is the square root of -1? They're strange because how can you take the square root of less than nothing? The intuitive meaning, again, we talked about the negative numbers being opposite, but for complex numbers or imaginary numbers, we're talking about rotation. We are looking at the next one, considered absurd until now, until you can fully understand them, which is a challenge. And multiplication cycle, or the general pattern for the complex numbers, 1, I, -1, -I, or x, y, -x, -y, and on and on. Use in coordinates. They rotate, which you can see that intuitive meaning, rotation, coming around again, rotate around origin. And you can see that these are rotating around the point of origin. With the orange one, we're talking about starting with 1. With the purple, we're starting with 2, even though it's not directly on it. And with the 3, we started at 3 and we rotated around the point of origin until we got all the way back. And we will break that all down in a little bit. Okay, and then measuring size. We're going to measure size with the Pythagorean theorem. We're not going to cover that in this, but that is how you measure it. So we're going to consider x squared equals 9. This is an equation that we're going to consider. And the question is, what number could you multiply by itself to get 9? Well, we could take 3. 3 times 3 equals 9, and then we have our therefore sign. Therefore, 3 squared equals 9. like x squared equals 9, 3 squared equals 9. And then you'll see here, x squared equals 9, which is the same as if we started with 1 and we multiply by x, and then we multiply by x again, we're going to get 9. It doesn't change the outcome. It doesn't change the product that we end up with. It's just that we're thinking of starting at 1. And the same thing, 1 times 3 times 3 would still give us 9. And just a notation on how times or multiplication can look like these, or they can look like these. But they all end up being the same. We're going to do a super quick review of multiplication. All right, so we're going to take 1 times 3. We would start at nihilo, or nothing, and we would end up with one group of 3. So we would start at 0, and we're going to make one hop or one group of 3, and we're going to end up at 3. 1 times 3 equals 3. If our equation was 2 times 4, we would say that it's the same as 2 groups of 4. So we would start again at our point of origin. We would make 2 hops, 2 groups of 4. There's one group of 4. There's another group of 4, and we would end up at 8. We could change that to say what I've been saying, which is 2 hops or movements of 4. So we would start at 0 and we would hop forward 2 times, as you can see here. 1, 2, at intervals of 4, with 4 in between. 1, 2, 3, 4. 1, 2, 3, 4. Going back to our 1.0 times 3, we'll start off at our point of origin, and we're going to make our one hop forward of 3, and we end up at 3. 1 times 3 equals 3. Now we're going to move on to our 3 times 3, or our 3 hops of intervals of 3. Starting again at the point of origin, 1 hop of 3, 2 hops of 3, and 3 hops of 3, and then we end up at 9. So we're going to consider now x squared equaling negative 9. If we were given that, like we were given x squared equals 9, we were able to come up with something. Now we're looking at x squared equaling negative 9. Well, we cannot multiply a positive number twice, x times x, because the result would be positive. We also cannot multiply a negative number twice, negative times negative, because the result would be positive. We cannot take negative 3 times negative 3 and come up with negative 9, right? It would actually be negative 3 times negative 3, and that would equal 9. So it doesn't work. And we also couldn't obviously take 3 times 3 because that is 9. Whoops, I did not mean to put that there. Okay, 3 times 3 equals 9. So neither one of those would work for that. How can you take 2 of the same thing and multiply it by itself to get a negative number? And here we go. Here's this example again. Negative 3 times negative 3 does not equal negative 9. It makes no sense. What can we do? Okay, so instead of considering x squared equaling negative 9, let's take the same x squared and make it equal negative 1 instead. Okay, x times x equals negative 1. How can we do that? Can you perform 2 multiplication steps and end up with a result of negative 1? Now, we could not do that to come up with negative 9. Again, the question is, can you perform 2 operations and get from here to here? Another way of saying that is, can you start facing forward, which would be like positive, and end up where you're actually facing backward instead? And can you do that with just 2 steps? Yes, you can. Okay, how do we do that? We do it with rotation. We do it with rotation. We're going to look at this number line. We are used to, especially with multiplication, with positive numbers, with negative numbers, adding and subtracting, And even with division, we are using the real number line. We are traveling left and right on the number line. And that is what we are used to doing for most of our starting math. Whether we're moving slowly by adding or subtracting, or we are moving faster by multiplication or division. Slowly, we've talked about this before. This is slowly. Okay, and then we get faster, and then over here we can use exponents, a number to a number, and we start getting even faster. Okay, so that is the number line that we've been using. Well, in order to start facing forward and get to where we're facing backward, and to do this rotation that we're talking about, we must have a different system. And that is where the imaginary number line comes into play. So again, we're used to using the real number line, and we're going to have to start adding in an imaginary number line as well. We are looking at the question again. Can you perform two operations and get from here to here, from the pink to the blue? We've talked about how 1.0 is going to be our starting point. When multiplying imaginary numbers, we are not hopping down the real number line or the reals domain number line. Instead, we are rotating around the point of origin. Okay, so let's just start doing it. We're going to start at 1, which is here. And when rotating around 0, we will be moving around at 90-degree intervals. Just think, if you're standing and facing east, by rotating 90 degrees to the left, you would be facing north. By rotating an additional 90 degrees, you would be facing west, which would take you from 90 to 180 degrees. You rotate again by 90 degrees to the left, you're going to be facing south. You've now made a 270-degree rotation. And if you rotate again to the left at 90 degrees, you've made a full 360 rotation, and you are now facing east again. So that's basically what we're doing here. We're going to start at 1, and we are going to multiply that 1 times I. 1 times I is 1I. That is a 90-degree turn from the 1 right here over to the 1I right here. So we've made a 90-degree turn, and we get 1I. If we rotate again, which is multiplying that 1I that we had here, we're going to start with it this time. Instead of starting with 1, we're going to start with our 1I. We multiply by I again. We've rotated an additional 90 degrees, totaling a 180-degree rotation, and we end up at -1 right here. So we've gone from 1, we went to 1I, and now we're at -1. So 1I right here times I is going to land us at -1. And that is a total of 180 degrees. And that is the same as our original piece of information here, that I squared is -1. The I squared is here, the I squared is here. The only thing missing at the top is the fact that there's a 1, like an assumed 1 or a hidden 1 or the implied 1, if you will, because 1 times anything is there. But it's necessary because we're looking at starting with the 1 and rotating from there. So we have completed showing how I squared equals -1. That everything kind of starts from is how in the world is I squared equal to -1? Because you have a negative and a negative, and that's supposed to equal a positive. Well, again, we are not working with the real number line that we're used to working with. We're working with rotation, and that makes all the difference. So we're going to move on. Now, up here we see the part of our paperwork that says to study the pattern and memorize. And we can see the pattern, including the number 1 down here, which I prefer. So remember, we started with the 1.0 or 1. That was the beginning of our I cycle. Okay, so we're going to move on. We're at the number 1. It is the beginning of our I cycle, we can see, and we have checked off starting with number 1. We are going to rotate by 90 degrees because, again, when you're dealing with complex numbers, you're rotating around the point of origin. So we're going to take that 1.0, we're going to multiply by I, and we come up with 1I, which is the same as I. And you'll notice right here, that is the next in the cycle of, oh, sorry, my hand's so shaky. That is the next part of our cycle, and we have checked off the equation that gets us to that next piece of information. Also, you can see we have rotated by 90 degrees. We're going to our next one, which is that we're going to take that I that we were at, which is right here, the 1I, which is the same as I. We're going to multiply by I again, and we're going to land at -1. -1. We have rotated by 90 degrees again. We are at a total of 180 out of 360 total degrees rotation. And you can see that we are in our third of the cycle, which is -1. And here you can see it up here. Okay, so we're going to continue on. This time we're taking that -1 and we're again multiplying by I. We get -1I, which is the same as -I, and you can see right here, -I is the next in our cycle, the next one in our cycle, and we have checked off the equation to get us there. We have rotated by 90 degrees again, and now we are at 270 of the 360 full rotation degrees. All right, so now we're going to take that negative oops, not that one. Can I undo that? There we go. Okay, we're going to take that -1I or -I, and we are going to rotate an additional 90 degrees, by taking that -I times I, and it's going to equal 1.0. We're going to land right back where we started. We have rotated 360 out of 360 degrees. You can see that we've started back at the beginning here at 1. And we have checked off that last step. And then we would just continue to go around and around and around and around by multiplying by I. So if we look at the copywork from the comparison chapter or comparison book, page 1, granted, it is just copywork. However, now we can understand it a little bit better. If we look at 1I equals I, which is the square root of -1, okay? So we're talking about 1I right here, and this is the same as the square root of -1. And we would just copy that down, obviously. But then if we look at I to the second, that was, all of these are based on starting with the 1. Starting with the number 1, if we did it to the first, which is 1I times, 1 times 1I. That's that single rotation, which gives us the I. This is the same as I. Then we're looking here, and we are making that second rotation. The second rotation, we're multiplying times I twice. I twice. Okay? So in this instance, we're taking 1.0 times I squared. So we made our first rotation. Now we're going to make our second rotation, and we're going to end up at -1. And here is your -1. So it's kind of like thinking when you look at these exponents here, it's how many times you're rotating from 1 or from 2 or from 3, because you absolutely could start with the number 4 and do these same things. If you started with 4.0 times I, where would you land? You would land at 4I. If you did 4.0 times I squared, you would be making 2 rotations right off the bat. You would start at 4, you would make your first rotation and your second rotation, and you would be at -4, the same as -1, but starting from 4. So again, the trick is looking at the exponents and figuring out how many rotations you've made. So we'll go over here to I to the third. That's making that first rotation we already made, the second one we already made, and making that third rotation, and we end up at -1I, which is the same as -I, and we would be here. Then we've got it I to the fourth. Well, that's 4 rotations. Starting at 1, 2, 3, 4 rotations puts us right back at the number 1 again. Again, if we were doing 4 times I to the fourth, that's 4 rotations around, and we would land, so it'd be 1, 2, 3, 4, I wasn't right on there, but we would land right back at 4 again.